Yeah, thank you everyone for tuning in, and thanks to the organizers for inviting me to present on the Corinth Rift fault network today. Today I'm going to be talking about the temporal and spatial variation in fault activity throughout the Corinth Rift fault network, the implications for the strain distribution, and then moving on to the seismic hazard assessment. But the work that I'm presenting today is an amalgamation of a huge effort from numerous collaborators that have been involved in the recent IDP expedition 381, which set sail in 2017 to drill the Sin Rift sediments in the offshore Corinth Rift. So I will also introduce some of the key data that the IDP expedition produced, because that has been used quite a lot in actually measuring and quantifying the fault activity throughout the rift. So firstly, to start with, why are we interested in the Corinth Rift? Well, the Corinth Rift is a very young and active continental rift, which began approximately 2 million years ago. It has quite a simple tectonic history, no overprinting tectonics, and approximately north-south extension. And the extension rates are very high. The modern geodetic rates are up to 16 millimeters per year in some places. There's also a high uplift rates that have been measured along the southern margin. And there's high levels of seismicity with numerous magnitude greater than 6 earthquakes occurring in the historical record and also within the last 50 years. This combined with high sedimentation rates and a near sea level position means that we are able to accurately and precisely record and quantify the deformation across faults throughout the rift. And we have a massive amount of data offshore now with a dense network of seismic reflection surveys and also the recent IDP cores, which I'll go into in the next few slides. All of this combined makes the Corinth Rift a natural laboratory for studying early rift processes at unprecedented resolutions. So moving on to the drill sites and the seismic data. Here you can see 2 seismic reflection lines. On the left-hand side here, if you notice, we have 2 seismic units. Seismic unit 2, where we have alternating high amplitude and low amplitude packages going through it, and a seismic unit 1, which lacks coherent reflectors and is generally low amplitude. And these 2 seismic units are separated throughout the rift by a regional unconformity, U here. Now, the drill sites focus on obtaining a high resolution chronology and environmental history of these 2 seismic units. Site 78 here targeted a condensed section in order to reach seismic unit 1 lower down, whereas site 79 targeted an expanded section of seismic unit 2 in order to create a high resolution core section through that unit. Now, the drill sites and the cores provided a treasure trove of data for us to use during the expedition and also for future projects, and also to help shed light on a lot of the previous studies and hypotheses that had been done before the expedition. To begin with, it actually told us what the offshore sediments were. These had never been drilled to these depths before, so we never really knew what was what the sediments, what the types of sediments were, and what they were made of at depth originally. One of the key things was that it helped identify 2 lithostratigraphic units, and these 2 units consisted mainly of different muds, but different mud facies. So in lithostratigraphic unit 1, it was able to be subdivided based on these different facies and paleo environments into marine subunits in blue here and isolated subunits in green here, when the basin was no longer connected to the Mediterranean. And below this stratigraphic unit, in lithostratigraphic unit 2, we had this very homogeneous mud that was also thought to be deposited mostly in isolated conditions. Now, what is really great about the data is that we had a numerous chronostratigraphic markers that we were able to pull out of the cores. To begin with, at the larger scale, we were able to do paleomagnetic analysis and identify paleomagnetic crons, particularly the Matayama-Bruns boundary at the base of lithostratigraphic unit 1, and also another subchron within lithostratigraphic unit 2, the Yaramillo subchron. But within lithostratigraphic unit 1, there are also a number of paleo microfossils which also shed light and provided chronostratigraphic markers throughout the core. And these essentially allowed us to correlate marine units with glaciostatic high stands on the 100,000 year cycles. So that provided us with quite a high resolution chronostratigraphy for these cores. And because we have excellent seismic data associated with them, we were able to do core log seismic integration and actually identify what horizons or packages within the seismic stratigraphy correlated with what we were seeing in the cores. And the first thing is that the unconformity between seismic unit 1 and 2 matched quite well with the lithostratigraphic unit boundary in the cores. And that basically placed an age of that boundary at approximately 780,000 years. And then in that upper seismic unit 2, we also had these alternating high and low amplitude packages, which I showed you on the previous slide. And these correlated, the high amplitude packages correlated with the marine subunits, and the low amplitude packages correlated with the isolated subunits, meaning that we were able to apply our chronostratigraphic framework to these seismic horizons. On top of this, we had velocity and porosity profiles for the cores, which allow us to depth convert seismic data and also decompact sediments offshore. So that kind of introduces the cores, but why is this important for the fault network? Well, using the seismic data that we have offshore, we use this RV Morris-Ewing data set, which has these numerous north-south profiles covering the majority of the rift, and they image all the way down to basement. Now, using, because we're able to use the core data, we're able to depth convert and decompact the seismic stratigraphy, and we're able to directly measure throws on most of the faults throughout the rift. But we're also able to apply the absolute ages of horizons to determine the slip rates or throw rates on those faults as well. One of the things that we did one of the problems that we did have with the Corinth Rift is that along the southern margin here, you have some of the largest faults within the rift, but their footwall is typically not imaged by the seismic data. So we're only able to calculate a minimum subsidence value for these faults. But because there's a huge amount of uplift data along the southern margin, we're able to combine uplift rates and subsidence rates from the same timeframes in order to calculate uplift subsidence ratios. And then we can apply that to these faults to calculate their overall throw rates. And just to give you an idea of the kind of uplift subsidence ratios that we were able to calculate for these major faults, for the Aliki, Deveni, Lycopori and Zillicastro faults, which are essentially these ones here. So I'll move my cursor along. We had a range of 1 to 1.1 to 2.6. So that's 1.1 to 2.6 subsidence to 1 uplift. The Parahora fault had a slightly larger uplift subsidence ratio, but that's thought to be due to the fact that it has a slightly lower fault dip in comparison to the other faults. But what was really neat is that these uplift subsidence ratios matched very well with those modeled previously by Bell et al. In 2018, where they showed a range of 1 to 3. And also this gray zone here is the previously published, there's two previously published uplift subsidence ratios for the rift. And so the majority of the data fits very nicely within that range as well.
Casey, you have 10 minutes now.
Thanks. So with the seismic data, we were able to map out very well the rift fault network, and we're able to show the basement faults very easily. That's what this map here shows. There's a basement depth map underneath this, which shows that there's overall a single major epicenter throughout the rift. Cumulative throw rates along these faults show a general bell curve shape matching the basement depth profile. And we can see that the north dipping faults in blue are accommodating approximately 2/3 of the deformation, whereas the south dipping faults are accommodating approximately 1/3. And you can see that we have numerous border faults here along the southern margin and along the northern margin. This is segmented border faults, which have at least 700 to 1,000 meters in basement offset accumulated on them. Now, if we have a look at some seismic transects along the rift, these three here, we can see that the rift structure varies spatially along the rift. In the west, it's accommodated by north and south dipping faults, and we can see that we have a general graben structure here that's formed quite nicely. Whereas in the central part, we see that there's both north and south dipping faults that have been active through time. So there's been a polarity switch. Below the unconformity, you can see that we have a northward thickening half graben, whereas after horizon 4 here, you can see that we have a south thickening half graben. So there's been a polarity change between 780 and 335,000 years there. In the east, we have a slightly simpler half graben structure where we're seeing a south thickening half graben since at least the unconformity. So how has this changed through time? That's one of the key, how has fault activity within this rift fault network changed through time? So here we have cumulative throw rates plotted in profiles. And what we see here is that through time, the first observation that you can see is that the overall throw rate of the network through time. So we're seeing more and more activity. We also see from A to C here, so from 2 million years to 130,000 years ago, there is an increase in the proportion that's accommodated by the north dipping faults and a decrease in activity on south dipping faults. Then in this final plot here, since 130,000 years ago, we see that there's been an increase again on the south dipping faults, and there's been a north dipping faults are maintaining their general cumulative throw rate. So why are we seeing these patterns of change? So what we're able to do, because we have such a detailed fault map and so much size and a dense seismic network, we're able to actually look at throw rates on all of these faults through time and how they change. So here for from 2 million years to 780,000 years, you can see that we have two epicenters, one controlled by this Galaxity fault here, and one further to the east, which is controlled by numerous faults. As we move further forwards in time, we see that there's a decrease in activity on the major south dipping faults. This Galaxity fault's decreased in activity, and there's been a slight increase on the north dipping faults along the southern margin. And we can see that the epicenter has grown and into a generally single large epicenter. As we move further forwards in time, we now see that the epicenters have essentially lined up along this southern margin. And we then see that the major faults along the southern margin are controlling these epicenters. And that continues through time since 130,000 years. But what we now see is that there are numerous faults along the northern margin that have started developing and they started deforming that northern margin. And it's related to the fact that we have so much localized deformation along the southern margin system. So this here quickly shows that southern margin system and how the slip rates through time have been changing. And what we see is that initially there's maybe two connected fault systems that are beginning to link, but they have quite low slip rates of less than 3 millimeters. But what a key point here is that since 335,000 years, there's been a huge jump in the slip rates along this southern margin fault system, up to approximately 5 millimeters. And it's now forming a bell-curved shape, indicating that it's quite a linked system. And that continues to the present day. So finally, what are the implications of a linked border fault system for seismic hazard assessment? Well, as you can see here, we've extrapolated our data set to the west and to the east, and you can see that the entire border fault system forms a coherent throw rate profile, indicating that it's probably a linked and coherent border fault system. We see a massive high in slip rates in the central part. However, if we have a look at the seismicity data that's plotted on the map here, you can see that there's very little seismicity in the central part. And in fact, most of the large earthquakes have been occurring in the east and in the west. Likewise, the highest geodetic rates are located in the west and not in the central part. And when we have a look at moment rate of the earthquakes over the last 50 years, we can see that there's been the lowest amount in the Central Rift as well, and the highest amount in the east. So this kind of begs us to wonder, well, should we be expecting a large earthquake occurring in the central part of the rift, seeing as the geological data suggests that it could happen? And if that were to happen, we might expect there to be a large earthquake system, a large earthquake sequence of maybe several large magnitude earthquakes, because we've managed to establish that this system is linked and the segmented faults here are linked at depth, just like in the 1981 earthquake sequence, which set off several of the fault segments along the margin. So here are my conclusions, and I'll leave them up on the board because I think we need time for questions.
That's what I wanted to suggest right now. There's a few questions. Gary Kana first, and then John Lewis second.
Thank you. I'm a little surprised by that this US ratio can really give any meaningful results. For example, given that the footwall topographic relief is a composite of all the extension events over the last 2 billion years or so, and maybe even residual topography, how can you tease out an uplift of the footwall relief to individual faulting events? Or am I missing something here?
Yeah, well, I should have mentioned maybe the timescales. If I go back to the first slide, because that shows the uplift data. The uplift are actually, these are averaged uplift rates, but they're in the immediate footwall of the large border faults going along strike. But they're averaged over over certain time periods in the late Quaternary. And they're often related to, for example, uplifted terraces in the immediate footwall of these large faults. And these terraces have been dated and basically are representing quite an accurate uplift rate. So the uplift data here is fairly robust in that kind of sense. And what we're able to do, because it's averaged over a long time period, it's not for an individual, they're not for individual events on these faults. These are averaged over long time periods. They're either averaged over 125,000 years, 240,000 years, or 340,000 years, depending on what terrace was identified in the footwall. Does that answer your question?
Thank you. It certainly helps. Thank you.
Next question is for John Lewis. Can you ask it yourself, please?
Sure. I'm curious as to, since you have maybe the luxury of core, do you have any core observations of faults that confirm your kinematics that that dip slip is in fact appropriate, because this complicated linking system, it's not too extraordinary to assume that there might be some somewhat oblique slip periodically. So are you assuming dip slip everywhere, or do you have some kind of core scale observations that help with that?
Yeah, it's a good question. We didn't see large faults in the cores as such, because we designed the drill sites to stay away from the faults, because we wanted a complete section of the stratigraphy. So we only had small fractures in the faults, and we're still looking at the orientations of those, but we for those that we were able to identify as tectonic fractures and faults, we were able to show that they were aligned approximately east-west in places. But majority of the information on whether it should be dip slip is actually from the seismicity data. There are focal mechanisms on these faults which show that they're dip slip, and also onshore there's lots of areas where the faults are exposed, and we're able to measure silicon sides. So that's been done a lot onshore as well.
Excellent. Thank you.